Okay, so you might be like, okay, we have all these equations, now what? What do I do with them? And the answer to that question is the whole point of thermodynamics is for us to figure out when a reaction will occur and when it will not. In Gen Chem 1, we're only looking at one part of that process, which is enthalpy. That is the first law of thermodynamics, right? And so it's important to remember some facts about what enthalpy is and really to understand the purpose, which is to figure out whether a reaction occurs or not. When we use the word spontaneous in science, spontaneous means can happen. Not that it can happen quickly, not that it happens kind of, randomly. We don't use the word spontaneous in science the same way that you would like in regular language. So I want to make sure you're clear that if we have concluded a reaction is spontaneous, that means it will happen. It doesn't tell you how fast. We don't get to learn about how to figure out how fast things happen until Gen Chem 2. It doesn't give you any kind of indication at what concentrations it happens. It just tells you that it can happen. But this is a really important first step for any kind of inventor, whether you're an engineer or you're trying to take concepts from biology and use those. You have to know whether a reaction is even possible before you can do anything with it. As it turns out, when you have a delta H that is large and negative, which also means exothermic, remember that phrase? When you have an enthalpy that is large and negative, it means that the reaction can happen. Okay, so we already went over this. This is Hess's law. Delta H of a reaction is products minus reactants. Now, it's important to also let you know that I'm going to add just one more symbol here. We want to add together all of the products enthalpies and all of the reactants enthalpies. Oops, I got this wrong. I'll correct this. Not reaction, reactants. Okay, so we use the symbol sigma, which always means the sum. Okay, and this is just like our final minus initial because that's, it's a delta. And so when your pressure is the same, in other words, when you were doing normal experiments on the benchtop in chemistry, you don't have a closed system generating gas, then you can actually use this equation. Okay, and the values for H are listed in a table that I've linked in a couple of places, and I will do it again in Module 4. But you can also find it in Experiment 7 as well. Same data table. Okay, I don't want you to search for random ones, because if you use different ones than the ones I'm using, we will get different answers. These are not ironclad numbers. These are measurements, and they take an average of a whole bunch of different measurements to get what is in the table. But if you go Googling it, you're going to get different conditions and different parameters in general. So be careful to use always the table that I give you to do the calculations. Okay. So here's one example of a reaction that happens to be large and quite negative. Do you see we're in kilojoules? So that's a big unit. And it's negative. That means that this reaction to produce water vapor specifically, is spontaneous and it will occur. In order to calculate this number, you need to have the balanced chemical reaction with the states. So if you've gotten a little bit lazy about that, it will not help you here. You need to know the state because the state of matter is going to dictate which delta H you choose from the table. So if you look at water, it will have one for liquid, it will have one for gas, and it may even include one for solid because, of course, we interact with water in all of those phases, right? They all have different values of delta H, so you have to know which one is pertinent. All right, now let's think about this. If we know that this reaction as it's written has heat of formation, formation means coming from its elements, right? Hydrogen and oxygen are the elements that make up water, so H2 and O2. So this reaction is the formation reaction for water, and it has an energy output, it's producing, because it's negative, of 483.6 kilojoules. That is a lot. It is actually an explosion. If you go on the internet, you'll find videos. It doesn't encompass the loudness of this because cameras actually deaden the sound. It's so loud. But anyways, if I had 4 moles of H2 and 2 moles of oxygen, and I made 4 moles of water, what would that do? Well, that's easy. You're just doubling everything, so we're going to double the amount of enthalpy produced, right? But what if we have a different state? What if our reaction looks like this? Same coefficients, by the way. What if we do 2 liquid waters, right? So just to run you through this calculation, I like to set up my delta H values from the table underneath my reaction so that I've labeled what goes with each thing. I would really appreciate it if you too would do that so that I can find the values you're using. That way, if you pull the wrong value out of the table, then I don't have to get all the points taken off because you've shown me where that came from. And if you do the math correctly anyway, you can get some credit. So the delta HF of 1 molecule of gaseous water is negative 241.8. And for liquid water, we're going to use negative 285.8. So in other words, it produces more heat, bigger negative number, to make liquid than gas. Okay, so we're going to use that. Whoops, wrong slide. There we go. We're going to use that in the same way that I already did to get this calculation, right? So here, if we go, this is the gas, so it's negative 241.8. So to use Hess's law, we're going to take the sum of all the products, which would be 2 times negative 248. I'm sorry, negative 241.8. This is kilojoules per mole, really, from the table, but I'm going to leave the unit off because I'm going to run out of space. I'll label it here. Okay, the reactants are elements in their natural state at room temperature anyway, which is what all these are measured at, 25 Celsius. They always have a value of 0. So here it would be 2 times 0 plus 0. So that's where negative 483.6 comes from. It's 2 times negative 241.8. Over here, the same idea applies, except we have negative 285.8. So our change for the reaction is going to be 2 times that number. Don't forget your signs, guys. That is the biggest mistake people make. And don't forget to use parentheses. Here it wouldn't affect your math, but when you do products and reactants that have values, it will certainly affect your math if you do not include parentheses for the reactants. Okay, so our total here is going to be 2 times negative 285.8. So we get negative 571.6. So just by having a liquid produced, and that, by the way, at the end you always want your unit. Just by having a liquid produced, we went up by almost 100 kilojoules, which is a lot. That's a big difference. So your state matters. Your state of matter matters. That's a funny pun. So make sure when you write your reactions, they are balanced and have a state based on either observation or the solubility tables or anything. Everything that we learned in experiment 4 is going to apply to this work as well. Okay, so this chart that I have given you is measured under standard conditions, which means exactly 25 Celsius. That's a bit warmer than our normal lab temperature. Our normal one ranges from like 21 to 22 Celsius. And at exactly 1 atmosphere of pressure. This varies on a daily basis, but the table is measured precisely under these conditions. When we say HF, that's formation. So that means 1 mole of the compound from its constituent elements, right? So when we're looking at the compound water, we used hydrogen and oxygen. So this whole thing, the way you read this, is the change in enthalpy of formation under standard conditions. It's a lot faster to write it like this. So the little circle means standard conditions. The F means formation from its constituent elements, making 1 mole of the material. And of course, delta H is enthalpy. All right, and so if I have a reaction that I can break down into 2 steps, it turns out Hess's law allows us to predict how to calculate the overall delta H without even having to know this middle reaction. So we just did that. We got negative 571.6. And let's see if we were right. So just like in the experiment 4 when you were doing the alum, to figure out the overall reaction, you look for what's the same on both sides, and you add the rest together. Right? So each of these steps is actually what's happening to form liquid water. Okay? And so to figure out the overall answer here, we're going to just take these 2 and add them together. Remember, this first one is just from making 2 molecules instead of 1. So we just doubled it from the appendix, from the table I gave you. The second one comes from comparing liquid and gas. So, once again, we get the same thing as we did by going products minus reactants for this reaction. This idea is we're going to use this in a worksheet, okay? And so we're going to look at some data, some different reactions combining together, and we're going to see if we can do the same kind of thing, where 2 different reactions can add together to form a third, and you should be able to add the energies of those 2 reactions together to get the energy of the third, all right? And so that's basically Hess's law, okay? Now, just for a concept check, is this negative or positive? It's negative, right? Two negative numbers are going to make a bigger negative number. And so then by extension, does that make it exothermic or endothermic? In other words, is energy leaving the system or is energy going into the system? I hope you picked exothermic. That's correct. Energy is leaving the system here. Explosively. It's fire and really big loud sound, and yeah, it's very much leaving the system. Where does it go? It goes to the surroundings, right? Okay. That makes this reaction, since it's large and negative, it makes this reaction spontaneous, which is good. We need water, and that's the only way to get it, is to make it. Okay. This is a bit more of an involved problem, okay? You need to know that gasoline is basically octane, which is C8H18, okay? And so you can write a balanced reaction for the combustion of octane. That's something we practiced. And then we need to figure out if we can find this value in our table. Okay, so it's unlikely. There's not a lot of carbon-containing compounds in here. You can see there's propane. You can see this one is pentane. This one is butane. This one is ethanol, which is what you can drink without poisoning yourself too badly. So we don't have any octane, which is very normal for these tables. So I'm going to show you another place where you can get that information. It's called the NIST web book. And this is a government run website. It is the standard, I don't know why it said that. It is the standard for thermochemical data. So anytime you need data, this is the best place to get it. However, you have to be careful that you are choosing the right state and the right material. Okay. So I'm going to use the name, and the name came from the question. We're going to call it octane. And so C8H18 is the one, and this is the structure of it. We'll learn how to draw these structures later. Now you want to pick the right one. You want to know, am I going to use this as a gas phase? Am I going to use it condensed, which would be liquid or solid? In reality, we usually burn octane as a gas when you have parts of your car that turn it into a small droplets of aerosol. And so we can use these values. It gives you the delta HF for the gas phase. These are pretty close together and come from two different sources, one from 1945, one from 1972. So I would choose these two. I would not choose this one because they have a note here that says it doesn't have the original data. It's not as good. So we can go with just these two, which is, basically negative 208.4. The rest of them are included in the table. So try out the problem and see if you get it right. There's going to be a link in Blackboard for you to submit your work. Be sure to use units, show your balanced reaction, and if you need to convert units, be sure to use dimensional analysis.